In this lecture, we shall consider work, energy, and power. Now, let us discuss what is energy. One of the fundamental goals of physics is to investigate something that everyone talks about, and this is energy. The topic is obviously important. Indeed, our civilization is based on acquiring and effectively using energy. For example, everyone knows that any type of motion requires energy. Flying across the Pacific Ocean requires energy. Lifting material to the top floor of an office building or to an orbiting space station requires energy. Throwing a fast ball requires it. We spend a tremendous amount of money to acquire and use energy. Wars have been started because of energy resources. Wars have been ended because of a sudden overpowering use of energy by one side. Everyone knows many examples of energy and its use, but what does actually the term energy really mean? The term energy is so broad that a clear definition is difficult to write. Technically, energy is a scalar quantity associated with the state or condition of one or more objects. However, this definition is too vague to be of help to us now. Energy is a number that we associate with a system of one or more objects. A short definition of energy can be the following. Energy is the ability to do work. Now, what is kinetic energy? The energy associated with the state of motion of an object. The faster the object moves, the greater is its kinetic energy. When the object is stationary, its kinetic energy is zero. If m is the mass of a body, and v is the magnitude of the velocity, of the body, then the kinetic energy is k is half mv square. Thus the unit of kinetic energy is is kg and v is meter per second. So is kg meter square per second square. So this is the unit of the kinetic energy. Now we discuss about potential energy. The energy gained by a body because of its change in state or configuration is known as the potential energy of the body. or state or configuration. If m is the mass, and say this is an example, and a body is thrown vertically upward against the gravitational force, so this is h, and the acceleration due to gravity is g, then the potential energy u can be written as mgh with respect to the ground. So this is ground and this is the height. So if a body is raised a distance h vertically upward, then the body of mass m will gain potential energy mgh. The unit of potential energy is the same as the potential energy, the unit of kinetic energy. So this unit is kg, and g is meter per second square, and this is h is meter. So you see this is kg meter square per second square. And I should mention here that the unit kg meter square per second square, both for kinetic energy and potential energy, is known as the joule. Or just in short J. I should mention here that this potential energy and kinetic energy that we have defined, they are the two variants of mechanical energy. We can have different types of energy. For example, this mechanical energy, heat energy, electric energy, magnetic energy, chemical energy. There are different types of energies you already know. Now we define work. Work is the force and the dot product between force and displacement. If there is an angle between the force and the displacement, if this angle is phi, then this is fd cos phi. Energy and work, they are scalar quantities. And you see the unit. So the unit of force is Newton, and this d unit of d is the meter. So Newton meter. Actually, if you convert this Newton, this is mass into acceleration. So kg, and acceleration is meter per second square, and this is meter. So is kg meter square per second square. So is joule. Okay, now let us suppose that we have a particle, and the particle is moving along this direction, and this the particle of mass m, and the initial velocity say is v naught, and the final velocity is v, and this distance is say d. Then the initial kinetic energy is half m v naught square, and final kinetic energy is, okay, let us say this is k, just square. Then if we find the change in kinetic energy of the body, and if we take common 1/2 m, so it will be v minus v naught square. But we know if the force is constant, that means if acceleration is constant, the equation of motion, we know this v square equal to v naught square plus twice d twice a is the acceleration and distance is d. So v square minus v naught square is twice a d. So if we put here, and this twice a d, then we'll have m into a into d. But what is mass into acceleration? We know this is force into d, and this is work. So for constant force, we now see the change in kinetic energy is nothing but the work done on the body. This is when the force and the displacement, they are in the same direction. Actually, later on we shall study this. The change in kinetic energy is nothing but the work done, and this is known as work kinetic energy theorem. So this theorem states that the change in kinetic energy is the change in kinetic energy is the work done Okay, so if the change in kinetic energy is delta K, and the final kinetic energy is Kf, and initial kinetic energy is Ki, then this is equal to work done W. And we have proved the work kinetic energy theorem in the case of constant force or constant acceleration just a few minutes ago. Okay, we shall come back to this work kinetic energy theorem later on. Let us first we define the power. Power is the rate of doing work. Or rate of transfer of energy. Since the work is force into displacement into the angle between the force and the displacement, so therefore the power P is the time rate of change of the work. So if you assume that the force is constant, then power becomes okay. Instead of d, if we consider that the displacement as say in the case of one dimension, let us say this is x. So along this direction is x, along this direction is force. This is phi. So fx cos phi, and this is dx by dt. We can say that this is f cos phi and this is v. Therefore, we can write down the power as the dot product or scalar product of the force and the displacement. I'm sorry, the force and the velocity here actually. And the unit of power is the rate of doing work, so is joule per second, which equal watt. Okay, now we shall find an expression for work done in the case of variable force. That means if the force is a function of position. say the force F is a function of position. Now for simplicity, we consider one-dimensional case. Okay, if we plot the force is a function of position, say we have this kind of figure. This is the force, and let us suppose that this is the initial position xi and this is the final position xf. The particle is under a force which is f of x, and our initial position is xi and final position is xf. If we now, the work done by this force is actually the area of the curve of f of x and the x-axis. So actually this is the work done by this variable force. Now if we divide this displacement xi to xf into some strips like this, and let us say we consider a particular strip, jth strip. J is 1, 2, 3, like this. There are a lot of strips we consider, and the average force on this strip is say F J average, and the width of each strip is delta x, say. Then the work done to cover this distance delta x, let us say this is Wj. So the force, average force into displacement distance. So force into distance is work done. To get the total work done from xi to xf, we'll have to sum up all these, smaller works. So the total work done this one. Now we assume that delta x tends to 0. If delta x tends to 0, then we'll have innumerable number of strips, and in that case then this summation will be replaced by an integral. So if delta x tends to 0, have to replace the sum by an integral, and the force is f of x, and delta x will be replaced by dx. Therefore the actual expression for the total work done by the variable force xi from xi to xf is this. So this is the general expression for the work done by a variable force f of x. Okay, now we prove the work energy theorem in the case of variable force. We have the work done for a variable force is, okay, for simplicity we consider one-dimensional case. And this one can be written as this. We can write down ma dx equal to m dv by dt into dx which can be written as and this is v. So if you cancel this on this, then mv dv. Let when x is xi, then v is vi, and when x is xf, then v vf. Okay, so if we change the limits and putting ma dx equal to this, then we can write down the work done. Therefore, the mv dv AC mv dv and this one can be written as so what we see? We see that the work done is nothing but the change in kinetic energy. This is the final kinetic energy and this is initial kinetic energy, so it's delta k. Therefore, delta k equal to w. We are now going to stop here. In the next lecture, we shall consider conservative and non-conservative forces, conservation of mechanical energy, and work done by an external force when friction is involved.